Welcome to week 8, the 8th and final week of mathematical methods for quantitative finance. This week I'm going to talk about numerical methods. So far in the course, I've introduced a lot of topics for solving different types of problems, but a lot of the examples and the homework have been what I sort of think of as toy examples, because they need to be complicated enough that you understand what's going on. At the same time, they need to be simple enough that you can actually solve them with a pen and a piece of paper. In practice, though, we're going to want to solve much more complicated problems. And so to do that, we're going to want to be able to do that with a computer. And so that brings us to this topic of numerical methods. So the outline for this week, I'll talk about a problem called implied volatility. So this is basically going back to the Black-Scholes pricing formula, but instead of thinking of the value that I want to calculate as the call price or the put price, I'm going to think that I could actually go, or I'm going to approach the problem in this sense. I can actually go to the market and I can observe all of the inputs for the Black-Scholes formula, and I can see what that put or call price actually is. And the one thing that's going to be the most difficult to observe is the volatility parameter, the sigma. And so given that I have the price, I can actually use Black-Scholes kind of backwards to figure out what the sigma parameter had to be to justify that price. And that turns out to involve solving something called a nonlinear equation. And so then in sections 2 and 3, I'm going to consider two methods for solving nonlinear equations, the bisection method. So essentially what I'm trying to do with the bisection method, so I want to find two endpoints so that I know I'm bigger than the value I want on one side and I'm smaller than the value I want on the other side. And then I'm going to just start chopping that interval in half, but preserving this property that the right endpoint and the left endpoint bracket the point that I'm looking for. And so as I chop this in half, the endpoints are getting closer and closer to the number that I want to compute. Another approach for solving this is called Newton's method. So this is it has a little bit stronger assumptions that I need the function I'm trying to find the value of to be equal or to be differentiable. And then the other nice property that Newton's method has is there's an n-dimensional version of Newton's method. So the bisection method is only going to work if there's a single variable. It starts to break down if there's a variable going this way and a variable going this way. And so once I've gone over how I can solve these nonlinear problems using Newton's method and bisection, then I'm going to look at some of the problems we had from last week's lecture. So in particular, problems that came up using Lagrange method. We're going to have generally a nonlinear system that we need to solve to find the critical point of the Lagrangian. And so we can use Newton's method to do that. So I'll talk about how you can set that problem up in section 5 and go through a small example. And then in section 6, I'm going to go through another example of that. And then finally in section 7, I'm going to look at the other optimal investment portfolio that I talked about in week 7, called the maximum expected returns portfolio. And so this ends up being a bit more complicated than the minimum variance portfolio, but it's something that can be solved using the n-dimensional version of Newton's method. And so I have an example of how that can be done.